Here we're going to look at what's called the laws of logarithms, and these are useful in applications and also in calculus. So let's start off by first letting little a be a positive real number, not equal to 1, and big A and big B both be greater than 0, and C be any real number. Okay, then we have the following three laws. So the first law says that the log base A, and A is any positive number not equal to 1, the log of a product, A multiplied by B, is equal to the sum of the two logs. So it's equal to log base A of big A plus log base A of big B. In other words, a log takes a product to a sum of the two logs. Second law, and I'm going to go ahead and prove the first law in a moment. Second law takes not a product, but a quotient. So the log base A of a quotient, A over B, that's equal to log base A of A, big A, divided by log base A of, let's rewrite that, that's looking a little messy. And it was wrong. Okay, so log base A of a quotient is log base A of big A take away log base A of B. In other words, log takes a quotient to a difference. So a product gets sent to a sum, and a quotient gets sent to a difference. And then the following third property, and this is probably the most useful property, property 3. It says that log base A of a power, so let's write that power as big A raised to the C. Now what happens to the exponent is it comes out front as a constant that we multiply the log by. So that's equal to C times log, log base A of A. So C times log base A of A. Okay, so a log brings that C down as a coefficient. Let's go ahead and prove the first law, and then we'll go ahead and see how these laws are useful. So proof of law 1, we want to show that log of a product is equal to the sum of the logs. Okay, first we're going to define, in this proof, we're going to define the number u such that little a raised to the u is equal to a, big A, and v such that a to the v is equal to b. Okay, now we can do that because, remember, a is the base of a logarithm, and it's a positive number not equal to 1, and here we're using it as a base of an exponential function. So remember, an exponential function has the range of all positive real numbers, and it's also 1 to 1, meaning that you give me a real number and I can find a u, or give me a positive real number and I can find a u such that a raised to that u is equal to a. So u and v are defined such that if you take u and you take a and you raise it to u, you get a, and v is defined such that if you take a and raise it to v, you get b. Okay, so with those definitions, what we're going to do is we're going to rewrite this left-hand side. So that means, using those definitions, that the log base A of the product AB is equal to log base A. Okay, and big A we're going to write as a raised to the u, so little a raised to the u, and big B we're going to write as little a raised to the v. So now, the reason that's useful is because it allows us to make use of the properties of exponents. Because these have the same base, we can add the exponents, and we get log base A of a raised to the u plus v. Okay, now we're taking the log base A of an exponential function with the same base, a, and by the cancellation property, these bases cancel and you just get u plus v. So from here to here was the cancellation property. For the two functions log base A of x and a raised to the x. That is, whenever you take the composition of a log function and an exponential function and they have the same base, then you get back to what you started with. In other words, I took u plus v and I raised a to the u plus v, and then I took log base a of that expression, and because the bases were the same, the two functions canceled, and I get just u plus v. Now, what is u plus v? We can isolate u and v by acknowledging that this statement is the same as log base a of big A is u, and over here log base a of big B is v. So remember, these are equivalent expressions. That is, you can convert back and forth between an exponential equation and a logarithmic equation. And you can check it, right? A to the u is a, and a to the v is b by those definitions. But the advantage here is that the u and the v have been isolated, so I can replace u down here with log base a of a, and I get log base a of a plus, and over here it's the v is log base a of b, so plus log base a of b. And that's what I wanted to show, right? Because it shows that the log of the product is equal to the sum of the logs, so the check means that completes the proof. Okay, now let's see how these three laws are useful. So first, let's evaluate the log base 2 of 8 raised to the 33. Now, of course, this is a very difficult problem, right? If you try to evaluate 8 to the 33rd power, that's some massive number. But remember, the most important property, the most important law is the third law, and it says that the exponent comes down as a coefficient. So this is the same thing as 33 times log base 2 of 8. And then we can evaluate the log, right? Log base 2 of 8 is equal to 3. So this is 33 multiplied by 3, and that's equal to 99, which is our answer. So that's the most important property of logs, is that the power comes down as a coefficient. Let's take another one. Let's expand using the laws of logs. So this is a log as well. It's the natural log, right? The base is e. It's unwritten, but the base is really e. Now the first thing I notice is that what the argument of the log is a quotient, right? It's something divided by something else. And so the first property I'm going to use is the quotient property for logs that says that the quotient gets taken into the difference of logs. That is, using property 2, this is equal to the natural log of 4x cubed, take away the natural log of the square root of 1 plus x. Okay, and then now looking at this, you might want to take that 3 out in front, but you can't quite do that yet because this is not a power. This is actually a product. It's 4 multiplied by x cubed. So because it's a product, what you have to do is use property 1, that is the product property, and you've got to separate these into a sum. So this is natural log of 4 plus the natural log of x cubed, and then minus the natural log of, now this can be written as, this next one as 1 plus x to the 1/2. That is, I wrote the square root of 1 plus x as 1 plus x to the 1/2. And now here it's the natural log of a power, so the 3 can come down, and same here, right? It's 1 plus x to the 1/2, so the 1/2 can come in front and gives us our answer, which is natural log of 4 plus 3 times natural log of x minus 1/2 natural log of 1 plus x, and that's our answer. So you might be asking, how do I know when I'm finished with these problems? And you know when you no longer have products or quotients or powers in the argument of the logs. Okay. Now, in this example, we expanded, but you can go the other way. You can take something like this and you can recombine them to get something like that. Let's see an example of that. So let's combine using the laws of logs. So the first one, I can see that now combining means you're basically using the properties in reverse. I can take that 1/3, which is out in front, and I can put it as a power, right? So this is going to become the log of x minus 1 to the 3rd, and then raised to the 1/3, right? So not only can I take exponents down, I can also take them up. And what I'm going to do in a moment is I'm going to multiply those exponents together. Okay, and for the next one, now you might say, let's do the same thing with the 1/2. Let's bring the 1/2 out in front. But you can't, because you can only do that. You can only take the number out in front when you have a single log, right? I don't. This is not a single log. This is a difference of 2 logs. So I have to take that 1/2 and first distribute it, and then I'll bring it up. So plus 1/2 log of x cubed minus 1/2 of log of x squared minus 2x plus 1 squared. Okay, so for the first one, the 3's are going to cancel. That's why I did it. So I have log of, it's just going to be x minus 1. Well, I didn't do it because they're going to cancel, but I did it because I don't want the coefficient in front of the log. And it just so happens that they cancel, so fortunately. Next one, they don't cancel, right? But we still bring it up. So it's going to be plus log of x raised to the 3/2, because 3 divided by 3 times 1/2 is 3/2. Here, the 1/2 and the 2 are going to cancel, right? Because it's going to be 1/2 multiplied by 2. And we're just going to write minus log of x squared minus 2x plus 1. And then the 2 comes up, and the 2 times the 1/2 gives an exponent of 1, which we just don't write. Okay, and then let's see. Now we can combine, now that we've taken care of the coefficients in front, now we can combine the logs using the product and the quotient rule. So going from left to right, the first thing I see is a sum, and that corresponds to a product. So I'm going to combine these and do that by multiplying these arguments together. So the sum of these two logs gives a single log. The log of, it's going to be x minus 1 times x to the 3/2. Okay, and the next one I still have minus log of x squared minus 2x plus 1. Okay, now it's the difference of two logs, right? So when you have a difference of two logs, you can write that as the log of a quotient. The log of this divided by that. So this is going to become the log of, okay, so all this is going to go in the numerator. It's going to be x minus 1 times x to the 3/2, and then divided by this. So x squared minus 2x plus 1. And let's put a parenthesis on there so we know what we're taking the log of. And now, of course, this can be factored. So it's going to be the log of, the numerator is going to stay the same. So x minus 1 times x to the 3/2. And that denominator can be factored as x minus 1 squared. Okay, let's change that back to a parenthesis so it looks, actually let's change this one to a bracket so it looks a little bit easier, it's easier to look at. Okay, and then finally a factor of x minus 1 cancels, and we have log of, in the numerator it's going to be x to the 3/2, and in the denominator we've got just one factor of x minus 1. Okay, and then we're taking log of that. So this would be our answer. So notice that I have a single logarithm, which is what we were after. We don't have a sum of two logs or difference of logs, and there's no coefficient out in front. So that's what we mean by combining using the laws of logs. Okay, in the next video we're going to talk about the change of base formula for logs. Until next time.